Okay, so last time I believe this is where we left off. You guys can correct me if I'm wrong. We were talking about convexity, and we defined convexity for sets. We talked about properties of convex sets. We talked about examples of convex sets. We talked about operations that preserve convexity, the functions you can apply to sets, and you get out a convex set. And then we talked about convex functions. And so here are the three important definitions for convex functions. I wrote down: convex, strictly convex, and strongly convex. This has to do with, if I look at the graph of the function at any two points x and y, then if I join the graph at any two points, the function has to lie below the line. The line joins the 3 points. And strictly convex just means that we get strict inequality. And strongly convex just means that the function is even more convex than a quadratic. So these are kind of increasing degrees of curvature. Here we're saying that the function has to be curved up in some sense. Here it has to be strictly curved up. And here it has to have bounded curvature from below. So not only is it curved up, but its curvature in some sense is at least m. Because when I subtract off this quadratic, m over 2, the norm of x squared, the function is still convex. And we gave a bunch of examples of convex functions. We talked about, I think, some obvious ones, some non-obvious ones. And then we stopped. Does that sound right? Okay, so I'll just say in words just to refresh your memory. Norms are convex. We saw that any norm is a convex function. The indicator function of convex sets are convex. So it's important that the set that underlies the indicator itself is convex. Quadratic functions are convex provided that the quadratic part, the quadratic form, that matrix is positive definite, or positive semi-definite. And this pretty non-obvious one, this guy, which we call log sum x, I'll try to come up again. This guy is also convex. Okay, so all the other ones except for this one would actually be quite straightforward to check from the definition of convexity. This one is not as straightforward to check this from the definition of convexity, but we're going to talk about some properties of convex functions, in particular another characterization of what it means to be convex. And we'll look at derivatives and second derivatives, and then it's actually easy to check this as convex. So today we're going to finish up talking about convex functions and their properties, and then we're going to hopefully arrive sooner rather than later to the punchline, why it's so important to know and understand convex functions in the context of optimization. So we'll get to optimization, we'll talk about optimization problems, and then I think we'll talk about subgradients, which are kind of like an extension of gradients, but for convex functions that aren't necessarily differentiable. And next time we'll talk about algorithms and a little bit of optimization theory, like the KKT conditions and duality. So that's the plan for this week. All right, so if there's no questions, then I'm just going to jump ahead and talk right into some key properties of convex functions. And so, by the way, there's a new document on the website, so you can go get that. I just added a bunch of sections to what was there on Thursday. Again, it's quite long. It's like the non-parametric regression notes. It has a lot more than we'll talk about, but that's just, there's stuff there in case you're interested. You can always read in more detail, or you can come talk to one of us. So we're just going to kind of flip through and talk about some highlights of this next couple lectures. So one of the key properties of convex functions is that a function is convex. So a function f is convex if and only if I can define a univariate function. So this might be a function on Rn. Maybe let's think about f. I think Rn to R. If I take essentially the projection of that function along any one-dimensional line through Rn, if that function is convex, then for all lines that I take, that implies that f is convex and vice versa. So if I define this function g of t be equal to f of x naught plus tb, so g is going from R to R now. So f is convex if and only if g is convex for any x naught in b. So if you give me any direction b and any offset x naught, I can define a one-dimensional function by just evaluating f along that line. And if that's convex for all such offsets and directions, then f is convex and vice versa. Okay, so convexity I can just kind of reduce to one-dimensional projections. And so this actually ends up being useful for proving that certain functions are convex. And proving that this is the case is not too difficult, but I'll just give you an example. Kind of a well-known function that ends up being concave. And okay, so by the way, we're going to be talking about convexity kind of throughout. Concavity, right? All the properties, you can just look at them and think, does it also apply to minus f? Well, if it does, then it's also an equivalent property for concave functions, right? Because remember, concavity, I can just think of this right here. For concavity, think about the definitions apply to minus f. So, right, I say f is concave if minus f satisfies this, it just flips the sign into inequality essentially. And f is strictly concave if minus f satisfies this, so again, satisfies inequality. And f is strongly concave if minus f satisfies this. Right, so all the same ideas apply to concave functions, and so the same properties will apply to it, right? I can just think about applying this to minus f, and then I get a representation for concave functions. It's really the same thing. So I'm not going to always say that, but just kind of recognize throughout that all the properties we talk about also apply to concave functions. So here's a function that's concave. So here's an example. If I take f of x, which is equal to the log of the determinant of x, so x is a matrix. If I take its log, then its determinant, this ends up being a concave function. Right, so if I want to be careful, I'll say that S goes from a set of positive semi-definite symmetric matrices to R. Or I guess maybe I have to say positive definite. So by two pluses, I mean that actually its domain is all matrices that are strictly positive definite, not just positive semi-definite. And so this is a concave function. Where would you have seen this pop up? Maybe some of the stats PhD students would have seen this. Where do you guys see this pop up? What's that? Graphical models. Yeah, so this comes up, for example, in the log likelihood of the multivariate Gaussian distribution. I'm just doing maximum likelihood for the multivariate Gaussian distribution. I do like the log of that, then this term pops up. If I'm maximizing likelihood, and I want to know that the maximum is well defined, then it should be concave. As we'll see, we're going to talk about optimization problems just in a second. But maximizing a concave function is well defined. Minimizing a convex function is well defined. So the fact this is concave is helpful because it appears, for example, in maximum likelihood for a multivariate Gaussian distribution. So how do we show this is concave? Well, actually, it would be kind of brutal to prove it's concave from the definition. But if we use this property, it's pretty easy. We just have to take, we're going to think about essentially taking this function, choosing some matrix X, choosing another matrix V, and proving that this function, which is one-dimensional, g of t, which is equal to the log of the determinant of x naught plus tv. If this is concave for every matrix x naught and every matrix V, such that this guy is positive definite, then that proves that log determinant of x is concave as a function of x. Okay, so we're not going to go through this calculation. Maybe I'll put on homework. I'm not sure. But here's just an example where it's very useful. Okay, now here come the smooth characterizations of convex functions. And so this is probably the one I think most people remember, or you end up using the most, because a lot of functions we end up dealing with are smooth. So here's a first order characterization of convexity. So if f is, let's suppose f is differentiable. So we're going to assume that. Then f is convex if and only if I have the following property. If I take f of y and I do a first order Taylor expansion around x, and I evaluate that at y, so I take just take f of x, I do a first order Taylor expansion, so I take the gradient, transpose y minus x. So this is like a linear approximation of f around x. This has to be an underestimate of the function. That's what this is saying. So this is true for any x and y. Then f is convex. Okay, so here's a picture. Suppose I'm at this point x. I do a linear approximation. Looks like this. If that's a global underestimator of the function, then the function is convex, and vice versa. Okay, so that's a characterization. Or if you want to remember more succinctly, the function always has to lie above the tangent line at any point. So that one's pretty helpful. Strict convexity, we just replace that with the strict convexity. Okay, so it's strictly convex if and only if that happens for any points x not equal to y. Okay, so that's in the notes. I'm just going to push on to the second order characterization. Now let's assume that f has two derivatives. So f is twice differentiable. Then f is convex if and only if I look at the second derivative of the matrix. Right, so the gradient is a vector. The Hessian is a matrix. Every entry is the partial derivative with respect to one variable. So the ith entry of this matrix is the partial derivative with respect to I and then j. It's a Hessian matrix. If this evaluated at any point x is positive semi-definite, then that's equivalent to f being convex. It has to be true for any x. Okay, so again, it may help to remember the one-dimensional case, right? It should be intuitive to you that if the second derivative is non-negative, then the function is convex. If it has two derivatives, this means that that function I drew here is shaped up. Okay, so these are really very useful. You know, we encounter a lot of smooth functions, and it's actually from either one of these perspectives that we end up checking convexity the most frequently. So how about strict convexity? Let me ask the question here. How can I characterize strict convexity for the second derivative? Is it true that f is strictly convex if and only if? Is this true? I'll write it here. F is strictly convex if and only if the Hessian is strictly positive definite. What do you guys think? I kind of hear something coming out of this side of the room, but I don't hear very clear. I can't even hear who's saying that, sorry.
I mean, if we don't have a Hessian.
Okay, assume it's differentiable. It's twice differentiable. So it has a Hessian. Is this an equivalence? No. Why not? Right. That's a great example. So actually, this is a common mistake people end up making, so I'm just trying to point it out. It seems like everywhere everything we do, strict convexity, just replace whatever the equality is with a strict one, we should be fine, but this is a common mistake. This is a sufficient condition. So if f is strictly positive definite, then it is strictly, if the Hessian is strictly positive definite, then it is strictly convex. So that direction is correct. The other direction is not. So if you happen to check whether the Hessian is strictly positive definite and it's not, doesn't mean your function is necessarily not strictly convex. Because this direction doesn't work. So Jisoo's example was a simple one. Let's just take f of x equals x to the fourth. That is strictly convex. If we go by the definition, this one up here, it actually does, it is sufficiently curved everywhere. But its second derivative at 0 is 0. Okay? That's just something to be aware of. Okay. Strong convexity characterizations, I'll just write them down kind of very quickly. Strong convexity gives us a bunch of interesting characterizations. Oh yeah.
So what are the conditions, in addition to strict convexity, ensures that the decision is always positively true?
Other condition.
So like if you are told that it's strictly convex, can you tell me something else and then I can conclude it?
That's a good question. Well, you want to be strictly positive definite, you're saying? You know that the function is, say, convex, and now you want to prove something about, or strictly convex, about its Hessian being strictly positive definite.
Yeah, I'm just asking this.
Yeah, I'm not sure that there is. I'm not sure that there is such a general characterization. I have to think about that. In most examples, you just have the Hessian and see for yourself if it can ever be singular. So strong convexity has kind of an interesting it adds something interesting once we know these definitions. So in particular, there is kind of an analog to the first and the second order conditions for convexity in terms of strong convexity. So let's assume F is differentiable. Then F is M strongly convex. Which means that it's strongly convex with the parameter M, if and only if. So look up there, we required the function to be bounded below by its tangent line. So its tangent line was always an underestimated function. For strong convexity, we actually get an even stronger lower bound. So we have the usual linear bound from convexity, but we actually require quadratic term as well. Okay, so it's saying that the function is not only bounded below by its tangent line, it's bounded below by actually a second order approximation where we use this as the quadratic term, m over 2y minus x squared. Okay, so this is really a much better connection. Like I said, when I said it's at least as curved as quadratic, this is a more concrete way of seeing that. And this ends up being both of these actually end up being a very useful tool to have if you want to prove things about, say, rates of functions like gradient descent and other kind of very classic functions. Classic algorithms end up using these representations a lot. And for twice differentiability, so assume F is 2 times differentiable, then we get the same thing, F is strongly convex, if and only if, again, it's a nice analogy to remember, we need to have that the Hessian of F at x is bounded below not by 0, but by actually the matrix m times I. Okay, so it means that every eigenvalue of the Hessian is at least m everywhere. Any questions about that? Okay, so there are a few more key properties. I'm not going to go through them because we really have a lot to cover, but there's a property that connects convex functions to convex sets. It's called the epigraph characterization. Because I'm not going to talk about it at all for the rest of this week, I'm going to skip it. But it comes up as an important fact in kind of various contexts when you end up doing convex analysis. So it's there if you want to take a look at it. It's a way of saying that a function is convex if and only if some kind of naturally linked set is convex. That set is called the epigraph of the function. Okay, so here are like I said, here's another kind of real important aspect of convex functions. Now we know what they are. We know some concrete examples of them, like the last time. We know a bunch of their properties. The last thing that we need to know to round off our capstone knowledge of convex functions is what we can do to them to preserve convexity. Because if we understand that, then if we have a very complicated function, we can take a look at it and try to see if it is built up of simpler convex functions by one of these operations. And then we can just say, oh yeah, it's convex, without having to go through any of these definitions, which can be quite challenging, especially if the function is complicated. So operations that can preserve convexity is kind of like the last fundamental bit of knowledge we need on convex functions. Okay, so these are operations. Preserving convexity. So the first one is just taking non-negative linear combinations. So if I have a bunch of convex functions, and I take alpha f1 plus, say, alpha 2 f2 plus alpha m fm, if these weights or these coefficients alpha are all non-negative, then this guy is convex, provided that all the functions are convex. So it is actually super important that they're non-negative, right? Because if I flip the sign of one of these functions, then it becomes concave. So I can't take arbitrary linear combinations. They have to just be non-negative linear combinations. This is a very useful one. This next one, so affine compositions. So if F is convex, and I have a matrix A and a vector B, then if I define a function g of x by f of ax plus b, then this function g is convex. So I can always compose a convex function with an affine function, and I still get a convex function at the end of the day. Okay, so well, I erased the one I want to talk about. We can also talk about this one. What happens if in here I put in something like trace of this function, log of determinant of trace of A transpose X plus B. So immediately we know that function is convex in X, because I just took this function and I composed it with the affine function that takes the trace of A transpose X. This is really like an inner product on the space of matrices. This is a linear function in X plus B, just an offset. Okay, so that immediately expands the set of functions that we know are convex to any log determinant of affine combinations of X. And I wanted to give another example of this one in use. So I erased it before, but remember the log sum exponential function was convex. So now we know that I can take log of the sum, say, of these functions. If I have any vectors ai and bi, that's still a convex function. So this is a pretty nice property to remember. It saves us from having to go back and check convexity in a lot of cases. No, this is the linear operator, yeah.
So it's for the sum of the eigenvalues.
So
this is sum of the eigenvalues.
the way you can see that is that the trace of A transpose X is actually the sum of AI, J, Xi, J.
But it's not just, it's not sum of all the values in the matrix, right?
It is, yeah. It ends up being the sum of all Ij. AI, J, Xi, J. It's really the inner product on the space of matrices. If you write it out, you'll see why that's true. The diagonal elements end up containing exactly those entries.
I think it's a little bit confusing because the case of A transpose X is a scalar and then B is a matrix. So
Oh, sorry. That is confusing. So I should have said this then. That's true. I could have put that and put B as a scalar, then I would have told you log of that is convex, the determinant of one-dimensional thing is convex, but I can just do this instead. Assuming that the dimensions work out, that's fine too. But thanks for catching that, that was confusing. Good catch. Okay, so I'm going to go through a couple more properties. That's those ones, or operations rather. So the next one is finite pointwise maximum. So if I have, suppose I have convex functions, again, say f1 through fm, like up there. I'm going to find this function f of x to be the maximum over all of my m functions. Then this is still convex. And so I'm not going to, we're not going to prove any of these operations preserve convexity. If you're having trouble believing anyone, you can't draw a picture and it's not making sense to you, then just try proving it, and then you can come talk to me if you're confused. But the point is just to kind of remember basic convex functions, basic characterizations, and then all these operations. That'll give you a huge dictionary of convex functions at the end. So this is convex. Right, so actually even more so than this is true. So I can also just take, I can take an arbitrary pointwise maximum. So if I define f of x to be, suppose I have convex functions indexed by s, where s is just some parameter. And I could have that this parameter lives in a set capital S that's infinite. It could even be uncountably infinite. It doesn't have to be even countable. This is still convex. If I take the pointwise maximum. Yeah.
Do these operations also like preserve the level of convexity? So like if you have something that's strict convex or something like
Good question. They all they all don't, not necessarily. So one thing to see right here, for example, is that this one cannot necessarily always preserve strict convexity. So why is that true? Well, let's suppose A was singular. A was singular in some directions, and the function is just constant in that direction. So it's definitely not curved in that direction. It's kind of a case-by-case basis. I don't know how much detail I put in the notes, but if you want that level of detail, then the reference to look at would be the Boyd and Vandenberg. Yeah, but good question. Most of them, I think you could probably work out what you need in order for the levels to be of convexity to be preserved. Okay, so this is nice. Actually talks up quite a lot also. We can take maxima of convex functions an arbitrary number of times, and it's still convex. So what's an example of that? Let's suppose I have some set C that's an Rn. And I'm going to find a pretty weird measure, but that ends up being useful in some cases, as a function of x, which is that I look at the furthest point in this set from x, say in Euclidean distance. Okay, I don't have to square it. It doesn't really matter, actually. So I claim that f is convex. The farthest point from in the set to the input x, it's a convex function.
C is convex.
No, C is not is an arbitrary set, not necessarily convex. So why is that true? Well, first let's look at the inner guy. This is a norm. So if I have just the norm of x, right, that's a convex function of x. So this is convex in x, the norm of x. But I don't quite have that. I have the norm of x minus y, and that's just an affine function. That's the norm of an affine function of x, right? I'm just subtracting off some constant. So I just think about the inner part. So this is still convex in x, this guy. Convex in x. And now I'm taking the the maximum over all these functions. Call these, we'll index these by y. F sub y of x. I'm taking the maximum over all these f sub y of x. I'm calling that f of x. It's still convex. I just according to that rule. So it doesn't matter if C is this set. If I look at the function which assigns to every point x the farthest point in the set C, it's still a convex function. Okay. On the flip side, let's look at minimization. So we looked at maximization and minimization now. So we'll have to consider what we call partial minimization. So let's suppose that f of xy is convex in xy. So it's really, this function is convex in its variable, but I'm just breaking it up into two blocks, x and y, for just so that I can write it more cleanly. So this function is convex, and I'm breaking up its variable into two blocks, x and y. If I take the function g of y, and I define this function to, I'll call it of x, so it'll be consistent with over there. If I take the minimum over all points y that are in a convex set C, of f of xy, then this is convex. Right, so it's more restrictive than over there. I can't just arbitrarily minimize, or partially minimize, and retain convex functions. I have to have a function that's jointly convex in x and y to begin with, so convex in its argument. And I can only partially minimize out away y over a convex set. So now let's go back to that same setup. Let's suppose I now have a set C, and I'm going to define the function f of x to be the minimum over all y in C of x minus y. So it's kind of like the flip side of this guy. So here I look at the farthest point in the set. There I'm looking at the closest point in the set. So this is convex also. But that's only true when we make the restriction that C is convex. All right, let's walk through this again. Let's consider this function on the inside. I'll call this I guess h of x comma y. I'll call this g, just so I'm not confusing you. So this is jointly convex in x and y, this inner function. Why? Well, because again, think about it like it's an affine transformation of the norm of the vector xy. I just take an affine combination where I do x minus y. Okay, so this is convex in its argument, xy. And I'm minimizing over a convex set, so according to our rule, what I get out, this function g is convex. But I had to know that the set C was convex for that to be true. So, if I look at now, right, the function that takes the closest point in any set to its input, that's convex. But there's actually quite a big difference for this function, which is always convex, if I take the farthest point. Okay, the next set of rules I'm not going to write down because they're really very specific, so I can't give you much intuition for them besides you just having to know that if you encounter composition, arbitrary composition, if you encounter a case where you have f of x is equal to, say, g of h of x, then in general, you have to be pretty careful here to make sure that f is convex. We can always compose with an affine function and retain convexity, but for arbitrary composition, the rules are very specific. So just make sure that whenever you encounter a situation like that, you go back to these notes or you go back to the textbook I referred you to, just look it up to see if you're in a case where convexity is retained. And the reason why they're specific is that we not only have to talk about convexity or concavity of G and H, we also have to talk about whether they're monotone or not. That ends up being important. So one example of a rule is that, I guess the notes I wrote like this, backwards. But one example of a rule is that if G is convex, so the inner guy is convex, and H is convex and increasing, then F is convex also. So there's a bunch of rules like that. Any questions about just kind of the basics so far of convexity for functions or sets? Yeah.
Sorry, did you say something about the connection?
I didn't. I can just write down. It'll take me just a second. So the connection is through this object we call the epigraph. So I just said it in words. I didn't write it down. Okay, and so the epigraph of a function is just a system function f goes from Rn to R. Then it's epigraph, which sometimes we write as epi of f. This is the set of all x comma t that's in Rn cross R. So this is going to be a set in Rn plus 1. The function lives on Rn. And it's the set of all pairs x and t such that f of x is less than 1 equal to t. So let's just go back to this picture. This is my function. It goes from R to R. The epigraph is in R2. It's in the set that's in space. It's one higher dimension on the input space of the function. And it's a set of all x t pairs such that f of x is less than equal to t. So it's all of this. It's this set, right? So the connection between convex sets and convex functions is that this is a convex set if and only if the function itself is convex. So in fact, everything we've said so far about convex functions, all their properties, they can all be proved by the properties of convex sets applied to this set. now I'm gonna attempt to if I've lost your interest so far with all this dry notions of convexity, I'm going to attempt to revive it to let you know why this is really so important and why you should really kind of study these concepts very carefully. And that's because when we talk about optimization problems, these become very crucial concepts. And to see that, it's very simple actually. So the next chapter of the notes is on optimization problems, and then we'll talk about that starting from now on. So an optimization problem is one of this form. So I'm going to minimize over all x some objective function we'll call f of x, subject to a bunch of constraints. And these constraints are going to look like h I of x less than or equal to 0 for I equals 1 through m, and L j of x equal to 0 for j equals 1 through r. So that's a very general form for an optimization problem. I'm not suffering any loss of generality by saying that it's min rather than max. If you told me, no, I like to maximize functions rather than minimize functions, then I'll just pose a problem like this, and it'll be the same problem. And so we can always talk about minimizing functions rather than maximizing functions. We won't be suffering any loss of generality from that. So this is called the criterion. These are called constraint functions, h, I, and Lj. The feasible set is a set of all points x that satisfy these constraints. This is all the terminology. So I say x is feasible, it means that h, I of x is less than or equal to 0, and Lj of x is equal to 0 for all I and j. And if x is a solution, it means that it's feasible, so it satisfies the constraints, and it achieves the lowest possible value of f of x among all of their feasible points x. Okay, so solution is the guy x star is feasible and it has this property that f of x star is less than or equal to f of x for any other feasible x. Again, just some terminology, and the last bit of terminology is that we often write f star to denote the criterion value at the point x star. So this is the optimal value of the criterion. It's the lowest achieved value of that. Okay, so really the interest in this problem is actually to find f star. Define x star. That's usually the interest in optimization problems, right? So you can think of tons of examples. If I took this to be like least squares loss and I had no constraints, it'd be like doing regression. If I took this to be, say, the logistic regression likelihood, or the negative logistic regression log likelihood, and I took these to be the component functions, so I have, or maybe the negative component functions, and I took these to be empty, then I have non-negative logistic regression. So I want to find the best classifier subject to every component of my coefficient vector being, say, non-negative. Or I can generate tons of examples of problems in this form. Everything we've talked about so far, in fact, can be put into this form. And everything that we'll see pretty much can also be put into this form. So what is a convex optimization problem? That's an optimization problem. Well, part of it is kind of obvious. We're going to need to put some constraints on these functions. F and optimization Lj. And so a complex optimization problem is one in which F is convex, and H1 to HM are convex, and L1 to LR, well, you're probably thinking I'm going to say convex, but actually this requires more than that. These have to be actually affine. So even if F is convex, the inequality functions are convex, if I happen to have an equality constraint that's not an affine constraint, then it's actually not a convex problem. Okay, so this is what makes a convex optimization problem. It's these three properties. So I can just rewrite it real quick so that we're clear about its form. It has to look like this. Equalities have to look like this. Maybe I can write AJ minus B equals 0. For J equals 1/3. So that's a convex problem as long as F and H are convex. And I can also be even more succinct and just write this as a matrix A times X equals B. Okay, so that's your generic convex problem where F and H are convex. Okay, just back to what I said before about flipping the sign of the criterion and making a max. A concave maximization problem is just one in which I maximize a concave function subject to the same set of conditions on these functions. So if I rewrite this as minus, maximize minus f of x, if f is convex, if the HIs are convex, and this is linear, so this is an affine constraint, then this is a concave maximization problem. We're not going to differentiate between that because it's just the same as doing this problem, which is a convex minimization problem. So it's just like when you've taken maximum likelihood, I can maximize the log likelihood or minimize the negative log likelihood. It's all the same. Why have I been going on and on about convex optimization problems? Well, there's a very good, we're going on about convex functions and convex sets. There's a very good reason for it. And we're going to state it and prove it right here, so it's not very complicated. And the following property holds for convex optimization problems is that any local minimizer is a global minimizer. And so we'll formalize that in just a second, but what it means is that if you're ever at a point where the problem is feasible and it looks like the criterion is as small as possible in some local neighborhood, so any direction you move is only making the criterion worse, then you found the solution. You don't need to search anymore, you found the solution. That's not true with non-convex problems. That is that's kind of the bane of non-convex optimization problems, is that you will tend to, in general, encounter local minimum, and you have no idea whether you have the solution or whether it's something that's just locally looking like the solution. Okay, so this is a very nice property, both analytically and also for the practical purposes of actually just computing solutions of convex optimization problems. This is a key property. And so here's the proof. We'll prove it right now. I think we can probably do it in this board. So let's suppose that x is feasible. So we're going to be working with this problem form. This is what convex correlation problems look like. X is feasible, and let's suppose it has the property that if I look at f of x and I compare it to f of y, for any feasible points y that are in some neighborhood of x, so if I just look at some ball around x, look at all the feasible points in that ball, and I say, oh, x happens to be the best in this local neighborhood, and this actually is going to imply that x is the solution, or it's a solution. So it's also the global minimizer. So here's the proof. And we're going to do it by contradiction. Now I think I haven't left myself enough room. It's not that short, but it's really short. So let's suppose that it wasn't true. Okay, so suppose in order to achieve a contradiction, assume that z is feasible, and I also have the property that f of z is strictly less than f of x. It means that x was not optimal. There was some other z that's better. Okay, well, then we're going to think about a point of the form. I'm not sure I get the 1 minus in the theta right. Yeah. So if I take 1 minus theta times x and theta times z, then we're going to look at points of this form for some value of theta between 0 and 1. So the first thing that we're going to claim is that this is feasible for any value of theta that's between 0 and 1. So why is that true? Well, obviously, if I plug in y here, I'm going to still get the ax equals b, or the a times y equals b, because I have ax equals b and I have az equals b, and then I just get 1 minus theta times b plus theta times b, so the equality constraint is preserved. And how about this guy? How do I know this is still preserved by sticking y? I don't know that hi of y is still less than or equal to 0.
Because the HIs are convex?
Right, just because they're convex. So actually, I didn't even need to go through this linear case separately. I just thought it might be more enlightening. But yeah, it's convex, so I get that h of y is less than or equal to 1 minus theta times h of x plus theta times h of z. Each of these are feasible, so they're both less than or equal to 0, and these are both positive, right? So I get that h of y is less than or equal to 0 as well. So this is a feasible point. So in other words, I'm saying that I've taken the line segment joining x and z, and I'm looking at all points in that line segment. They're all feasible points. Okay, so that's one thing. Now here's where the contradiction comes. Coming in one other step. So let's now look at also f of y. Again, just by convexity at f, right, because it's a convex problem, I have that this is less than or equal to 1 minus theta f of x plus theta f of z. Let's suppose we end up choosing theta strictly between 0 and 1. Then this actually ends up being less than f of x, strictly. Why? Well, because this thing is strictly less than f of x. Okay, so now I've just said that on the line segment joining x and y, I can actually beat x in terms of the criterion value as long as I don't just go to the end of the segment for any point in between that line segment. So where's the contradiction now? Right? So it's a local minimizer, but
So the points in the neighborhood around x were supposed to be.
right, I can make this y arbitrarily close to x. Right? And then I have a point that's in that neighborhood, x minus y, norm less than or equal to r, that's beaten x in terms of the criterion value. And so all I said is that here's x, I had a neighborhood of x in which it was optimal, but any point on the line segment joining x and z actually has a better criterion value than x. Well, that's a contradiction, because then I can just take a point on the line segment arbitrarily close to x, and I've contradicted the fact that it's a local minima. Okay, so no such point z exists, which means that local minima are global minima for convex optimization problems. Okay, another point of confusion. Let me make this clear now. Does this mean that there's only one solution to a convex optimization problem? Can there be multiple solutions? Why? Yeah. Right. So yeah, this does not mean that there's a unique solution to a convex optimization problem. It just means that anything that's locally optimal is globally optimal. But here's an example of a convex optimization problem that doesn't have a unique solution. Every point x is a solution, right? So there's it's definitely not a local, a unique solution to this problem. And there are much less trivial examples where the solution can be non-unique. Just think of, for example, this convex function. Right? If it's flat here, any of these guys are solutions. So it does not mean that the solution is unique. Sometimes people remember this and say, oh yeah, convex problem is just one solution. That's not true. It means that any local minimizer is a global minimizer. Maybe a better way of thinking about this is that a convex problem always has a convex solution set. So a convex problem will give you a convex solution set. So the set of points that minimize the convex problem is itself a convex set. So we didn't prove that. That is, it follows from essentially just the exact same arguments as this guy. Okay, so that's something to remember. The last thing is that if the function f happens to be strictly convex, so if f is strictly convex, and it's a convex problem, then this does imply that the solution is unique. Okay, so now you see the importance of convexity because it means that any local minima is a global minima. Now you've seen the importance of strict convexity because it means that there's only one solution to the convex problem. The criterion value is strictly convex. Okay, again, we didn't prove either of these last two statements, but they follow from virtually the identical arguments to the one we just gave for this last case, straight from the definition of convexity. Okay, so now with the hope is that we see a problem written down, has a complicated criterion function, has complicated constraint functions, but we can recognize whether those are convex or not, because we have the tools to do so at this point. And then if they are convex, we know that this problem is going to have good properties. We know that, for example, it can have a local minima that's not a global minima. It maybe has a unique solution if the criterion is strictly convex. And we're going to see a bunch of tools, maybe towards the end of today or next time, that's going to inform us a lot more about properties of the solution, algorithms to find it, and stuff like that. But we're just setting up to get there at this point. Any questions before we take a break? Yeah.
Anything stop the solution from being negative to infinity? Like it's linear now.
Yeah, it doesn't. That's fine. We're not really paying attention to that at this point. But if the function is what we call coercive, then it means that the solution is not ill-defined like that. It exists within the interior of Rn. And so coercive just means that if I take any ray from, say, the origin pointing out into space, I have to make sure that the function doesn't diverge along that line. If it's, let's say, lower bounded along that ray, then it's coercive. So yeah, it means we can't have functions like straight lines. It has to be lower bounded along rays. But we're not really bothered by that. I mean, it's still fine for the purposes of optimization. When we talk about algorithms like gradient descent and stuff like that, then we'll be a little bit more careful by saying that the function has a solution that exists in the interior. Any other questions?
Is it like, I was thinking about the proof of partial minimization. It's not as intuitive as like global maximum convex.
Maybe we should offline. I think that would probably be better. But the partial minimization, yeah, it helps to see, I think, a couple of concrete examples, but we can talk about that offline. Okay, let's take a break. We'll come back and talk about subgradients this semester, so I forget when they finish, but that's not a good excuse. Oh, actually, I also want to point out one other thing, which is, somebody asked me a question last time, and I thought about it. I don't remember who the student was. Maybe it was you. You might ask me this question. And I said something wrong, so I wanted to clarify that. So the question was, when we talk about the convex hull, the convex hull of a set was the set of all convex combinations, right? We said it was like theta 1 x1 plus theta k xk, such that k is bigger than equal to 1, and x1 to xk are points in the set. Oh, the theta is at the sum to 1. And b non-negative. So that's the convex hull. And I think somebody asked me last time, can I just take 2? Can I just take k plus 2? And I said yes, but I thought about it after class, and that was definitely wrong. So here's why you can't do that. Well, let's suppose we have 3 points. What's the convex hull of this set? It's just a triangle, right? So it's actually all of this. So what happens if I just take the definition of convex hull, but I only allow for combinations of 2 points? What do I get? I just get the border of this, right? That's all I get. I can only take convex combinations that have 2 points. So it's definitely not the same thing. I have to allow for arbitrary combinations. Okay. That was kind of a tangent, but I wanted to make sure that nobody took me on faith and wrote a paper and then got rejected or something. Okay, so here's what a subgradient is. We're going to talk about subgradients next time, and then a bunch of algorithms and more advanced stuff. Subgradients, I like to think about it, it's like calculus, but for grad students. That's what I'm going to tell it. So in high school, you learn calculus. In undergrad, you think it's like calculus is old news. But in grad school, it comes back with a vengeance. Subgradients are the analog thing. And it's super, super useful. It's really useful stuff. I would claim it's like the rest of this. But essentially, the definition of a subgradient is just like we saw for convex differentiable functions, except we're just going to say that a function f has a subgradient g, so g is a vector. So it's an Rn if the function goes from Rn to R at a point x. When I take the linear function defined by g, this lower bounds the function f everywhere for every y. So I need to know that f of y is equal to f of x plus g transpose y minus x. Remember, for a convex differentiable function, we knew that if I took g equals the gradient of f of x, this helps. So it tells us that for a convex differentiable function at x, its subgradient is the gradient. Okay, but we can have cases where the function is not differentiable, but it still has subgradients. So what's an example of that? Obviously, one sector is, let's write this down. So let's suppose this for our function is not differentiable at this point, but it has a bunch of subgradients at that point. These are just really any of these vectors, right? Any such vector like that, that when I take the linear approximation, plugging in that g, and lower bound the function, those are all subgradients. Jersey, do you have a question?
So g depends on x?
Yes, it's a subgradient g at the point x. So we're going to write it like this. G is an element of what we call the subdifferential of f of x. Okay, so I'll just say the property in words. If f is differentiable and convex, then it only has one subgradient at every x, and that's the gradient. So in the case that f is differentiable and convex, subgradients are gradients, no difference. If f is differentiable but not convex, it need not have a subgradient at all its points. I can have arbitrarily smooth functions that don't have subgradients. Right? We can think of many examples of that. But for example, just take the function x cubed. It's differentiable. There's no subgradient at 0. Yeah, I can't think of any single linear approximation to the function there that's going to lower bound the function everywhere. And a very nice property of convex functions is that they always have subgradients at every point. So at any point of a convex function, differentiable or not, we know that's true for a differentiable convex function because we just take its gradient. But for convex functions, at every point x, they always have a subgradient, at least one. And for those of you who were in the class last semester, you'd like a challenge because you've seen this stuff before, perhaps, you could try to prove that. So you can prove that from the definition of convex sets and by using the supporting hyperplane. Okay, so it's a very nice construction for convex functions. They always have subgradients. And so we'll see next time why they're so important. We'll go into the details next time.